Well, I'll go ahead and go.
There you go.
Okay. And I think just to warn you guys ahead of time that there's at least one or two places where the animations occurred at the wrong time, so be prepared. Just sort of as a segue, my boss with the U.S. Geological Survey works very closely with NIDIS, Jim Verdon, and so the material that I'll be presenting is in some ways similar to both the previous talks. I'm going to both look at trends in drought, particularly in Africa, but also a global context of food security. But I'm also going to have some thoughts based on the U.S. Agency for International Development's Famine Early Warning System Network from a more practical perspective, with a particular focus at trying to integrate information and impacts across scales. So my name is Chris Funk. I work for the USGS, and I'm also a researcher at the University of California, Santa Barbara. So it's a little bit of a RISA kind of situation where we get kind of ongoing funding from USAID to do applied climatological research to support famine early warning. We work closely with Eros Data Center, more and more with NOAA ESRL, in part because of Jim Verdon's presence there. And one of the unique things about our research team is that we have field scientists that are permanently stationed in Guatemala, Niger, Kenya, and Gaborone. And so that gives us a really unique opportunity to develop new drought early warning science, test it out in Africa and Guatemala, get feedback. And that's one of the things that makes it pretty exciting. And really, there's a lot of two-way flow. So there are new tools and applications that are developed in Africa that are flowing back to the United States and both ways. Okay. So I think this next slide is the one that has a problem on it. So we're going to start with the good picture, which the slide back here is something you don't want to see anyway. It's a very, very hungry child from 1984, 85, taken in Ethiopia when more than 1 million people died due to drought. As a response to that, the Famine Early Warning System Network was set up, and we've been monitoring conditions ever since. The picture here was taken in 2009 in southern Ethiopia. The drought in 2009 was every bit as bad, or perhaps worse, than the drought in 1984, and the humanitarian response was very effective. So that doesn't mean we don't have problems, but drought early warning systems can really have a powerful effect and save lives and reduce the economic impacts of water scarcity. The kind of thing that FuseNet does is make maps like this. What happened is this was supposed to come at the last slide. So bear with me. But this map here is taken from the FuseNet website from last week. And what we do now is we are constantly updating maps of this nature. And so it has a food insecurity phase indicator here, going from no food insecurity up to catastrophe or famine. And what we're trying to do is prevent things from getting catastrophic. And you can see that in a large part of the eastern Sahel, and this is Ethiopia, Kenya, Somalia, situation is pretty bad. And we also routinely provide these 3-month outlooks, and unfortunately, we think it's going to get worse in Eastern Africa. So this isn't good news, but it's better that we're providing this information now instead of reading it in the paper 6 months from now. So the focus of my talk today is the idea of looking at water deficits across many scales. And so at a local scale, I think we're all pretty familiar with these ideas that you can have poor rains or high temperatures over the space of a few weeks, leading to crop failures. If that goes on too long, that can produce livestock mortality. On the course of months, you might have a failed crop that can lead to hunger or reduced income. And as that goes on, that can impact, I can't point at that. If that goes on, you'll have increased poverty and health of the households that you're dealing with. And this could be a household in Indiana or a household in Kenya. And if this occurs over time, that can lead to a cycle of poverty, which can make households more vulnerable. There's less money in the bank, there's less reserves to deal with the next crisis, and that can also degrade ecosystem services. You can have land degradation, soil depletion, right? So what we want to try to do is have effective mitigation before you get to here. And if you think about how things can be integrated regionally, right? Of course, you can have these regional or even continental droughts, which Professor Sang gave some great presentations on this morning. But if you have these things going on over time, right? You can have drought and the impacts of drought feed into population growth, because the higher infant mortality, you tend to have more children, right? It can lead to malnutrition, and it can even contribute to frailed states, which a lot of the policy people are concerned about being one of the greatest threats that we're facing in the 21st century. You know, we're not so much looking at a future that's going to be nuclear warfare against half the world against the other world, but it could easily be, you know, that over the next several decades, we find increasingly there's more states that are really struggling to meet the basic needs of their people. And the recent spike in commodity prices has really added fuel to that fire. And I'll talk a little bit about that. And, you know, at the sort of largest scale, in some ways, the recurrent impacts of drought can weaken states. And if you get enough weak states, then we have a weak global governance. And if we have a weak global governance, then how are we going to, you know, deal with tough issues like global warming? So, you know, one of the things that we can do to try to address these problems is to improve our monitoring systems. And, you know, this is basically my day job as a geographer and a climate scientist. And here, you know, in Africa, we work a lot with satellite data because you can get it, it's easy to, you know, to see, and you don't have to rely on a lot of monitoring in terms of in situ observations. And it's great stuff. You know, with the new MODIS vegetation indices, with infrared observations of rainfall, microwave observations of rainfall, it's a tremendous resource to monitor what's happening in terms of drought in near real time. And luckily for us, seeing when it doesn't rain is about the easiest thing to spot from space. It's hard to tell how much rain you get if you get a lot of rain, but if it's just darn hot and sunny, the satellites really do a good job of picking that up. But where we really have a problem is integrating from weather into climate. So, you know, the satellite record is short, tends to be inhomogeneous, and so, you know, it's really hard for us in places like Africa where we're relying on these things to say, like we can say for Texas, this is an historic drought. And so I think that's one area that we can try to make advances. And another one that we really need to advance on that's perhaps more important than the scientific techniques, and I think NIDIS is really a premier institution for this kind of advancement, is getting better about sharing information, you know, sort of at greater spatial scales and over time where you have decision makers who are going to pull the trigger and lead to effective mitigation and adaptation. But I would also argue that those agencies need to get better about using that information to trigger effective responses. I know personally that the FuseNet people that I work with, we really feel like over the last 5 or 6 years we've made pretty tremendous advances in our ability to provide effective early warning. And the response from the decision makers has not been very effective. So, you know, of course, maybe they need to take time to see that we can provide useful information, but it has to go both ways. There need to be improvements with information flowing up and decisions flowing down. And then also this idea of global drought monitoring, which Doug mentioned. Actually, we just got funded with Mike Brewer on a global SPI product. So, you know, maybe we'll be working towards that together in the future. But of course, this is an increasingly important challenge because food, you know, really travels in terms of price information on a global scale. As I'm sure most of you know, drought isn't just a shortage of water. Well, it is a shortage of water, but that shortage is composed both of supply and demand. And so one of the things that we do in FuseNet is pay attention to the temporal and spatial variation of demand. And of course, at a local scale, crop efficiencies, tillage practices, right, are going to change how the water demand changes. But over time, population growth, increasing temperatures are also going to play a role as well. And thinking about how those things can integrate over regions, we're going to have increasing water demand, right? More straws in the cup. For the Colorado Basin, I think, is an excellent example of that. That can lead to conflict, or it can lead to successful adaptation. Of course, as Professor Sang mentioned, new demands such as biofuels, right, are also adding to our demand for water. And again, if we integrate to sort of the largest realm, this increasing demand that's coming from population growth, biofuels, more people eating meat, can lead to higher prices and perhaps also less political freedom. As we're struggling as a sort of world in general to meet our basic needs, the more energy that's going into that is the less energy that's going into teaching our children. So these are really important issues to try to deal with effectively. So in FuseNet, one of the things we try to do is map vulnerability and water exposure, water use exposure. So this is just an example of how we think about water demand in space. This is Ethiopia, and basically it goes from the very dry Somali region over here up into the highlands in the northwest. And the green areas here are places where the households get enough water, right? And even in a region here in the central southwest, where they get a lot of rainfall, the population density is so high that they're still water insecure. And so, one of the things an effective drought early warning system needs to do is have a good idea of these spatial patterns. So if there's a shock, right, say a rainfall anomaly expressed as a standardized precipitation index, that's going to have very different implications here than if it happens here. Another thing that's really playing a big role in terms of underlying demand is global prices. And so unfortunately, between about 1969, this is from an FAO report, over the last 40 years, from 1969 to say about 2005, the number of undernourished people in the world stayed about even. About 850 million people, okay, went chronically hungry to bed every day. Unfortunately, on our watch, that number has jumped up to perhaps over 1 billion. I think this FAO projection for 2010 is probably a little inaccurate. This probably came out before we had the really hot summer and cereal price increases that we've seen. And so, unfortunately, while we did a good job of bringing down the number of undernourished people until the 2000s, that's really stagnated. And I think we really have some major concerns about where that's going to go in the future. I'll do this really fast because it's already been mentioned. June of 2010 was exceptionally hot. That led to fires and a near-failed crop in Russia. Russia closed down their exports of grain. The price of grain increased by about 30%. So when that happens, there are billions and billions of people in cities all across the world who spend 70% or so of their income on food. So when the price, if I go to the store, I honestly wouldn't notice if the price of milk, right, or the price of a loaf of bread went up 30%. But if you're paying 70% of your salary for that, then that's a huge food stress. And so, the policymakers are really worried about that contributing to political unrest. And this is a picture from Cairo of somebody lighting a car on fire. So you can't, it's like attribution. You can't say that this guy lit the car on fire because of warming in Russia, but there are really important implications of food stress on a global scale. And what's different about this, and which is a real challenge to agencies like the Famine Early Warning System Network, is that prices now communicate risk globally. It used to be you could watch your weather data, you could find a drought, and you could go to that area and respond to the drought. This is a whole new problem that requires this integration across scales. Another concern that we have, and this is from a paper that I had in food security, is that if we look globally, this is for the globe and these are for different parts of the globe, we can basically look at the amount of food produced per person, sorry, not food, but cereals per person, right, and express that as yields times the harvested area per person. And you multiply those two numbers and you get cereals produced per person, okay, which is a crude measure of food availability. But the concerning thing is that if we look at the trends in this, you know, these are for the globe, but you can do this for any of these large super regions. You know, we find that yields have been going up. But however, both because population is growing so quickly and because things like urbanization are eating into the available cropland, we're finding that for many large parts of the world, the per capita harvested area is declining faster than yields are going up. And I would argue that these would probably even be somewhat optimistic estimates because, well, that's another talk. Anyway, but if you just take these values and project out into 2030, not very far away, we might see a decline in the per capita cereal production, taking us back maybe to the early 70s. And this sort of food availability limitation would be compounded by the use of biofuels, by meat consumption, and things like that. So I would suggest that this is one part of the price spike that we've seen recently, which luckily for farmers in Indiana will be a great thing. So, but the global implications are problematic. Of course, drought is also a function of water supply, and we can think about you know, how we can have deficits across the meteorological scale, agricultural drought. You can have repetitive agricultural droughts, right? Like the tendency to have more droughts in the 1980s and 1990s than we had in the 1950s. And if you get enough of those, then you can think about that as a drought trend. One of the things that I do for FuseNet, in collaboration with Matt Barlow, who's helped us out, is try to link those observed climate trends, okay, particularly in Africa, to larger scale climate patterns and ask ourselves whether those might be related to global warming. And so I'll talk a little bit about that. That kind of analysis really forms this kind of a priori type of work, vulnerability identification work that you want to do before you enter a growing season. Okay, you want to know what the population, rainfall, and temperature trends are doing, how they impact water and food availability, and how that plays out in space and time. Then when you come into a season, there's really different stages that you go through. You know, before the rainy season, you can issue a kind of forecast. What's the outlook? Then as you go through the season, hopefully you will update that, right? And then finally, you get into the mid-season assessment, where you sort of have progressive stages of certainty that you've had a significant drought. And so really, you know, I think from this context, it's important to realize that drought isn't a switch, right? It's a state of mind. And to, you know, monitor drought effectively, you know, you basically start here where you're going, oh, I don't know, this area might be prone to drought. And then you come here and you say it's Indian Ocean Dipole event or El Nino or La Nina. So at this point, you're activating your network of people who can respond if something happens, right? So you've put in place your contingency planning. Then as you get to the season, you know, you can monitor, and probably there's a ton of experts in this room who are the ones that can really say, oh, now we really know it's a drought. But to really use this information that you have it here, you need to get ahead of the curve and forewarn people so that you can have a timely response. Otherwise, you get to here and you say, oh, there's a drought in Texas, and it takes 6 months to respond, and at that point, you know. So in terms of the long-term trend analysis, the work that we do is really distinct from things like the IPCC. We don't look a lot at coupled climate models. We do look a lot at observations of observed data on the ground in Africa, and also in the climate, in terms of the responses of observed climate variability. And what we do is we try to piece those trends together. And what our research has suggested is a story that's very different than what the IPCC advances. The IPCC advances, and Aguayo Dai's work is, I think, a representative of a lot of that, suggests that it's going to get wetter in East Africa and drier in Southern Africa, a kind of classic El Nino response, which seems to be recreated by a lot of the IPCC models. And that could be true, but it's very different than what we've seen over the last 30 years. And unfortunately, we've seen a lot of drying in Ethiopia, Kenya, Tanzania, Sudan. The most food insecure people in the world are being impacted by this drought. And research that we've carried out has suggested that this is tied to warming in the Indian Ocean, which is increasing rainfall. So what we think is happening is that this heating in the Indian Ocean is causing air to rise over the southern Indian Ocean. And as this air rises, it moves and it basically creates greater stability over the greater Horn of Africa and over the northern Indian Ocean. Okay? And what's concerning for us is that the Indian Ocean is, as far as we can tell, and this is really a conclusion that is appears coherently across basically all the observational data sets and all the climate models, is that as the globe warms, the Indian Ocean warms. And so just looking here at global temperatures back to about 1875 and Indian Ocean sea surface temperatures back to 1860, they really seem to co-evolve in time, and both of them have this big jump after 1980. Okay? And again, this is something that appears in many, many data sets, this sort of hockey stick response. But I'm very concerned because this is going to affect the people that I've been trying to watch out for the last 10 years. And so if we look at the correlation between March, April, May, and December, January, February rainfall in these areas, this is Somalia, Ethiopia, right, all the way down to, this is Zambia, Zimbabwe, and Botswana. During the boreal spring, which is the main rainy season for Eastern Africa, there's a strong negative correlation between rainfall over the Indian Ocean and rainfall over Eastern Africa. And a similar pattern, though displaced to the south over the December, January, February season. So what we're seeing here is, in a sense, an enhanced hydrologic cycle, right? You're getting more rainfall, but that rainfall is occurring preferentially over the ocean and bringing dry subsiding air over these food insecure places. And this is basically borne out by a canonical correlation analysis between rainfall and wind patterns and the community atmospheric model forced with diabatic heating. Matt Barley did this stuff. And so where it really looks to us is that as you increase diabatic forcing and rainfall over the Indian Ocean, I don't know if you can see the winds, but you get this overturning circulation that makes East Africa drier. This work was mostly looking at December, January, February, and March, April, May. We're just in the process, then we had another paper that came out looking at that season as well. This is Park Williams and myself in Climate Dynamics, which basically showed that looking at the first principal component, which is the element that explains the most variance of vertical velocities between 60 and 150 west in this box of the Indian Pacific. So zonal winds, 2-meter temperatures, and precipitation. The single most important component of that was surprisingly not El Nino, but something that is very akin to climate change. This is global temperatures, this is that component. And what really looks like there's a large westward extension of the warm pool. This area of very warm SSTs is extended very far to the west, and this appears to be a robust result from all the coupled climate change models and all the observational data sets that we can get a hand on. So it appears that something similar is happening in the summertime, where we're finding big increases in evaporation tied to these increases in SSTs over the southern Indian Ocean, because there are very rapid surface winds there. So it's this warming under very rapid surface winds by the equator that's creating this large response that appears to be creating an overturning circulation from the southern Indian Ocean and the northern Indian Ocean, which is, our concern is that this is disrupting the northern Indian Ocean monsoon flow. So normally winds come this way and feed into East Africa and the northern Indian Ocean, and it looks like that's becoming disrupted by this warming and evaporation in the southern Indian Ocean. So that's kind of new work, but it's pretty concerning, not just for Africa, but perhaps for India as well. And now we can skip this one. So one of the things that we're trying to do is guide adaptation. So you can get this information, but how do you get people to use it? And so this is a graphic that we've developed for USAID to try to move this information back up, the chain of command to have people using stuff. So this is Kenya. This is where people grow crops. This is the 500 millimeter isohyet on average between 1960 and 1989. So basically this corresponds quite well to where people grow most of the crops. The polygon here is showing our best estimate of where this contour line lies now. And so this contour line has contracted towards areas with higher elevations, leaving millions of people exposed basically along the flanks here. And if this trend continues, who knows, but it could, given the link to the warming Indian Ocean, then even more people are going to be exposed, particularly in eastern central Kenya. And so one of the ways we're hoping this information can be used is to guide where people are going to be doing agricultural development. Clearly, your agricultural risk is going to be a lot less here in the future than probably here or here. I'm going to end with just a few more slides on the monitoring this season, and then I'll wrap up. So over the last 12 months, we can think about how FuseNet responded to different degrees of drought certainty. And so the concerns began in August of last year, where we happened to be at NOAA, and NOAA said, oh, that's it, there's going to be a La Nina. And in part because our prior research had suggested that climate warming in the Indian Ocean increased the impact of La Ninas, and also because we knew that East Africa had had really bad rains in 2007, 2008, and 2009, we basically put out a report immediately. And just looking at historical outcomes, you could see that about half of the times that there have been a La Nina, there have been back-to-back droughts. So East Africa gets rain in the fall as the sun passes, and then again in the spring as the sun passes. So there's 2 rainy seasons. And about half of those in recent years, when there's been a La Nina, about half of those seasons had back-to-back droughts. So we didn't do anything fancy, we just looked at the data, but we put out this report saying, watch out, this could happen. Unfortunately, this did happen. We've developed, with NASA funding, this Early Warning Explorer, which allows us all kinds of cool zooming and clicking and time series and intercomparison of different data products. And here we're looking at land surface temperature anomalies for October, November, December of last year, and the satellite rainfall anomalies for the same time period. And unfortunately, it was really bad, and almost a total failure of the rains in a lot of the eastern sector. And then during this last spring, it was hit again. And so right now in June, we've basically just finished passing this information up the chain to USAID, and the information that we got back was, yet again, this keeps happening. And so there's sort of this drought fatigue that's been going on. So one of the things that we've tried to do, and I think that one of the things that DryNet is trying to develop, believe, is this idea of uncertainty estimates. And it would be great if we can include that in some of our work, that kind of idea. But what we've done here is looked at these pastoral areas in Kenya, southern Ethiopia, and blended satellite-based rainfall estimates for the last 10 years with interpolated station data back to 1950. I did this work. I'll admit it's a little bit uncertain, and we should really try to bound the errors, but this was a fast, real-time decision-making context. But to our best ability, it looks like for many of these districts, this has been a historic drought. And if you look at both seasons together. And so, I think, I wish all of this was wrong, but I think that this example provides a good segue of how you go from, sort of pre-drought, where you look at trends and spatial patterns of vulnerability, to a seasonal context where you're getting ready based on El Nino, La Nina, things like that, NAO, to mid-season, where you're saying, oh, this is bad, and then to this kind of placing it in a historic context. And so those are all pieces of effective drought early warning. So in terms of happy thoughts, there really is a lot to be excited about. I think that the science has really advanced, and I think we'll continue to advance it. At the same time, this network world really allows us to communicate this information really rapidly, and that's tremendous. Another thing that I think is often overlooked is the idea of consilience, of having multiple players come to agreement, right? And I think the American Drought Monitor is a great example of that, because decision makers don't like to have different stories. But if you get all the smart people to come up with the same one, you're going to get a lot better responses. And of course, our climate, hydrologic, and crop models keep improving and allow us to integrate this information effectively. We'll all spend, or not all of us, many of us will spend our lives trying to advance these things, but I think, we've made a lot of advances already. Of course, there are very big concerns out there. The demands for water are increasing. Our per capita food supplies are decreasing. And at the same time, the market system exposes billions of people, many of them urban poor, to food risk and food stress. And as our work for Eastern Africa has perhaps shown, an enhanced hydrologic cycle may bring drought to people even at the same time as evaporation is going up. So, thanks.
Question, perhaps you can have the discussion with Chris during the break. But indeed, if there's a burning question, please feel free to ask one.
Now, I think most of your work is based on MODIS products. And have you applied Landsat, and have you looked at the gain in information by going from MODIS to Landsat?
So I work for Aeros Data Center, which obviously does a tremendous amount of work with Landsat. But we haven't used Landsat very much in terms of the early warning response because of the time delays and sort of need to do it quickly.
That resolution improvement must give you better information, perhaps?
Well, I have to, so recently, the Aeros folks have just put up a continental 250-meter eMODIS product for Africa, which is, to me, that's pretty high resolution. You could, that's, and which is really about all you could do at a continental scale.